All right. Should have time today to get the test back to you and let you see those. I did not put them in the grade book yet, but I will probably get them put in the grade book today. And then tomorrow is a review day, and Wednesday or Thursday is our next quiz. So if you're going to be gone tomorrow, let me know. I can get you the review ahead of time so that you have that. Anybody going to be gone tomorrow? Anybody need that? Okay, today is a new type of function, which are log functions. And log is short for logarithm. And I won't use the word logarithm very often, but if you ever heard the word logarithm, I always call them logs, and I don't really use the word logarithm. There's actually two different kinds of logs that we're going to go over today and talk about. But the first thing we're going to do is kind of talk about what is a log, where does it come from, why do we use a log, what's the purpose of it, and how is it a function. Okay, so the graph is a function, and just like every other function that we've done throughout the entire semester, is it passes the vertical line test, right? When I graph it, it'll pass the vertical line test, and all of the things about it would be the same as what we talk about with any other function. So yesterday, we talked about the exponential function. The exponential function, we said, could be something like y equals 2 to the x. So a log function is essentially combining what we did on Friday and what we did yesterday together to make a new function. And so if I did the inverse of the exponential function, my equation would be x equals 2 to the y. Because on Friday what we said was in order to do an inverse, we're going to flip-flop the x and the y. X and y are going to trade places. So I'm going to take the function we had yesterday, and we're going to trade places. Well, all's well and good, right? X equals 2 to the y and whatever, but if I wanted to write this as its own function, and I wanted to write this in the form of, in some case, even be able to use my calculator now to be able to write a function and graph this function, I can't put this in like this, right? In order to be able to graph it or do some other things with it, then I would need to get it in the form of y equals something. And so we're going to take this function, x equals 2 to the y, and we're going to change it to a log function. And when we change that to a log function, then we would write it like that. Two is the base. The base of the exponent is the base of the log. It's the first thing we're always going to look at, and I'll say that a lot. The base of the exponent and the base of the log are always the same thing. My exponent is the number that comes over here. So we're going to say 2 raised to the y equals x. So the log is really the only thing that gets inserted there, and we're just rewriting it in a different form. So rather than writing it like this, we can now write it like this. And by putting it in this format here, then we could be able to use our calculator, we can graph it, and we can do a lot of things. So there's a lot of benefit of writing it. But the biggest thing is it's in y equals form. It's its own equation. It's its own function, okay? In some cases, I might even say f inverse of x equals log x base 2. Going back to what we talked about Friday, the inverse of the original function, the inverse of this exponential function is log x base 2. Okay? Remember, f of x and y are interchangeable, but I just want you to really understand why the log is what it is. Tell
What actually changed on the inverse?
them. The X and the Y trade places, right?
Would you put the X or that 2 or next to the 2 then, the Y?
Do what now?
Like log 2Y, or would it just be? If we were changing them?
If we were changing them, so like to write this one is this, okay? Then whatever the base of the exponent is going to be the base of our log. If we're going from our inverse equation,
Okay.
okay? So this is a subscript, rather, so like an exponent is like a superscript. It's raised, whereas a subscript is going to be lowered. So it's going to be like underneath the log. And so we're going to talk about like the basic format and how to write it, but in this case it's a number, but we're going to talk about it in other situations too. But yeah, it's a subscript, so it's not like one continuous equation. It's a little bit lower than that. And there's a lot of different ways that we could say this, and I don't really know what the right or wrong way is. Some people say log x base 2, some people say log base 2 of x, means the same thing. One thing that stays consistent is we call this our base, okay? So log base 2 of x, log x base 2, we want to say the word base because that tells us that it is the subscript in that case. And it's not just like, if I write log 2x, that's a completely different meaning than log x base 2. So putting it there as our base is a big thing. Okay, now, when we do this, and this is going to be like probably one of the most important things that we're going to do as we talk about logs, and eventually we're going to talk about solving log equations and things like that. If I were to write out an exponential equation, and I'm only going to do this with variables. The first one I did it with numbers so you could kind of see what's going on and where it comes from. But if I said x equals a raised to the y power, this is an exponential equation. And today we're going to do a lot of going from exponential to log or vice versa. And so that's why I'm drawing the arrow either way. If I give you an exponential, I should be able to write a log equation. If I give you a log equation, we should be able to write an exponential equation. So if I were to rewrite this as a log equation, I'm going to write the log first, okay? The base of the exponent is the base of the log, and that's our subscript. And that would be usually the first thing that I would put in. Okay, and then we call this the circle rule. I can do a raised to some power. So a is being raised to the y power. So that's the variable that comes over here. A raised to the y power equals x. And another way of rewriting that is y equals log x base a. And that's why we call it the circle rule. A raised to the y equals x is just rewriting that original exponential function into a log equation. Okay, sometimes they'll give us this. There's going to be times where the exponential equation is better. There's going to be times where the log equation might be better. But we're going to do a lot of trading back and forth between those two. But this right here, I'm going to put a big star on this page because this is extremely important. Okay, being able to go from a log to an exponential or the other way is going to be critical in a lot of things that we do. And we'll keep coming back to this and talk about what is the basic rule of logs, and then let's change it to an exponential or vice versa. Bless you. Okay. Another thing that we can do sometimes is we can use this to evaluate. So if I had some problems here where I ask you to evaluate. And I'm going to give you some different variations here. If I had log of 9 base 3, and I ask you to evaluate that, okay? Now typically, they don't write equals X or something over here. We're just trying to figure out what goes in this space right here. But if we use that exponential rule that we just talked about, I could rewrite this as 3 to some power equals 9. We're just using our circle rule, right? And I'm just putting a box in there because that's what we're trying to solve for. I'm not putting X or anything else like that in there. I'm just saying what is going to go in that box. Now we can solve this, right? I can say 3, we know 3 squared equals 9. So log 9 base 3 equals 2. And it's just a whole number. Okay. I will tell you this. I know that some of you guys, you've done logs in Algebra 2. Some of your calculators have a log base button. Some of them don't, okay? And the newer ones, that's a new thing that they've added to some of the TI calculators. I'm going to show you ways to get around that if you don't have that button. But some of you do have the log base button, and I know you know where it's at, but there's going to be times where it's helpful, but sometimes I'll show you ways to get around that as well. Okay, if we have log of 10,000 base 10, and trying to figure out what that equals. Once again, trying to figure out what's going to go in that box. 10 to some power equals 10,000. I think that's going to be really hard, right? Well, think about it this way. If this was 100, 10 squared would be 100, right? If this was 1,000, 10 cubed would be 1,000. So basically, every time we add a 0, we add another exponent. And so this would be 10 to the 4th equals 10,000. So log of 10,000 base 10 equals 4. Okay, and we'll talk about this more later, but if there is no base, your base is assumed to be 10. If we want a base to be here other than 10, we have to put it here. If I don't put it here, we assume that base to be 10. Okay, so these two things are the same thing. So you wouldn't necessarily have to put that 10 there. It's kind of like having X, right? If I have X and I don't have a number in front of the X, we know that's assumed to be a 1. If I don't have an exponent on the X, I know that's assumed to be a 1. We have some assumed coefficients or exponents. And in this case, if we have a log, my base is assumed to be 10. So if you ever put it into your calculator as the log, and so on this one, if you want to get your calculators out and if you type in the log of 10,000, it'll give you 4. And that's because it's assuming your base to be 10. If you want the base to be something else, then we have to put that base in. Okay, here's another evaluate problem. 5 to some power equals 5. And these are all ones that we should be able to figure out the exponent, and there's going to be times where we aren't going to be able to figure out this exponent, okay? And we'll talk about why we use logs and stuff like that here in a little bit, but 5 to what power gives me 5? This would be 5 to the first. So log 5 base 5 is 1. Whatever that exponent is what it's equal to, and that's our evaluate. Some of this, we kind of have to remember some of our exponent rules, which we haven't really talked about for a while. So on this one, we're saying 6 to some power gives me 1. So if we have an exponent, and my answer is 1, what exponent do we have to have? 0. Okay. 6 to the 0 power is 1. Anything to the 0 power is always 1. Doesn't matter what my base is. So my base down here could be anything I want it to be. It could be 6, it could be 600. Doesn't matter what the base is. If we're doing the log of 1, then my exponent always has to be 0. Okay, this one's a little tricky. Mainly because of the way it's written. Okay, but once again, we kind of have to remember some of our exponent rules. How would we read this decimal right here? 0.01. 1/100th. Yep. And so I think it's actually helpful. Bless you. To rewrite it like this. 1/100. And you can write it as 0.01, but 0.01 and 1/100th are the same thing, okay? So I think the fraction's a little bit easier here, and here's why. I got to get my base 10 to 100. Well, 10 to what power gives me 100? 2, okay? But where's the 100 at? It's on bottom, okay? What makes us move a number to the bottom? What kind of exponent makes me move a number to the bottom? A negative, okay? So this would have to be 10 to the -2. So this would be negative. Negative exponents make me take the reciprocal, okay? So 10 squared is 100, but to move it to the bottom, it's got to be negative, okay? So just kind of a couple of, and I know we haven't talked, like I said, we haven't talked about some of those exponent rules for a while, so that's kind of another thing that kind of gets thrown in the mix here where we got to kind of remember some of those exponent rules that we've talked about in years past. Okay, this is one we're going to see from time to time throughout this chapter. Nine to some power equals 3. And here's another exponent rule that, once again, we haven't talked about this one for a while. Like, let's say even without exponents. What would I typically say I could do to 9 to get to 3? You could square root it, right? But if I take the square root of 9, then we have an assumed exponent of 1, and we have a root of 2. A square root is always an assumed root of 2. So the square root of 9 is the same as 9 to the 1/2 power. We call that a rational exponent. My exponent is a rational number. It's a fraction, okay? So when I say the square root of 9, 9 to 1/2 is the same as that. Those are interchangeable. It's kind of like 1/2 and 0.5 are interchangeable, right? One's a fraction, one's a decimal. If I say 9 to the 1/2, I could also say the square root of 9. And those are the exact same thing. So here we would say 9 to the 1/2 power equals 3. So log 3 base 9 equals 1/2. We don't want to put a square root in there. We want an exponent as our answer. And so that's why the 1/2 is better than the square root. We know the square root of 9 is 3. And so we can use that rule as part. And so just kind of remember that rational exponent rule. We don't see that a ton, but it will be something that comes up off and on throughout this chapter. Okay, so those are just some different things of using evaluation, and we're going to talk about some of those things again here as some basic rules. We're going to use some of those evaluation things that we just did to write a couple of log rules that will hold true for any log. I'm going to put down the one that we just talked about again, okay? So, and it doesn't really matter what side you put this on. So I'm going to put log on one side. I'm going to put exponential on the other side. I'm going to show you some rules where if I give you a log, we can write it as an exponential or vice versa. So if I said log of x base A equals y. And I'm going to draw those arrows again, going back and forth from one to the other. We're going to take that log equation and we're going to write it as an exponential equation. And once again, that is our circle rule. A raised to the y equals x. And that's my exponential equation. Okay, all we're doing is rewriting it and something like that. We're not solving or anything like that. Okay, if I had 16 equals 2 to the x. Oops, I put that on the wrong side. That's my fault. That would be the exponential form. Okay, when we write this one out, we're changing it to a log equation. Okay, once again, the base of the exponent is also the base of the log. So that's my subscript. My base is going to go down here, base 2. My exponent is going to come over here. And once again, we're doing that circle rule. 2 raised to the x equals 16. So it really doesn't matter what side of the equation the log's on. Sometimes the log might be on the right or the left. It's still the same equation. I could flip-flop that if I want to. I could say log 16 base 2 equals x, and it's the same equation. Kind of like x equals 3 and 3 equals x. It really doesn't matter what side the x is on. Okay, and I'm just throwing some random variables in here. These variables really don't mean anything. All we're doing is taking a log equation and rewriting it as an exponential equation. So in this case here, m raised to the a equals q. So when I rewrite that exponential equation, everything is there except for the log. The log comes out. I'm going to rewrite it exponentially, and we don't have a log in it anymore. When I write it as a log, we're going to take the exponential and we're going to insert the log. That's the only difference between the two, is do you have a log or do you not? The log equation has a log. Exponential obviously does not. Hey, we could even do it where we have all numbers. I could say 2 to the 5th equals 32. So it doesn't matter if it's letters, if it's variables, whatever it is, we can do this with anything that we have. I always like to write the log first. You can do it kind of however you want. I like to write the log first because I know I'm writing a log equation, so I'm just going to go ahead and insert that log in, and then I just go through everything that we have. My base is 2, so I'm going to insert the base first. Base of the log is 2. 2 to the 5th power equals 32. We're just using that circle rule. 2 to the 5th is 32. And that just kind of helps us the path that we're going. 2 to the 5th is 32. And you can do it the same way over there. Okay. So on those, we're just going back and forth, talking about rewriting it in a different format. Okay. I'm going to put a couple of things down here that we talked about a few minutes ago. If we have a 1 right here, and I wanted to figure out what goes in, or what is this equal to? Well, we talked about it up above. If this right here is 1, if I take the log of 1, basically what I'm saying is something raised to this power gives me 1. What exponent will always give me 1? 0. Okay? So it does not matter what my base is. If I have a 1 right here next to the log, my answer is always 0. okay? I can put whatever number I want down here. So that's a rule, right? That's one of my rules that we should know. If I see a 1 next to the log, I always know it's going to equal 0. Bless you. Okay, another one. That's a big one. If these two are the same number, same variable, whatever, if these were both 8, let's say I put an 8 in here. 8 to what power gets me back to 8? 7 to what power gets me back to 7? 1, right? So if the log and the base are the same number, same variable, then my exponent or my log will always equal 1. And so that's another one I'm going to put a star by that we should know. Okay, so those are some of the basic log rules. If you want to get your calculator out, we're going to do a few things on our calculator as well. What we talked about earlier was these two things are the same thing, okay? I don't have to put a base 10 in. If I don't have a base on my log, my base is assumed to be 10. So the reason I write that is because I want you to know, obviously, that it's assumed base 10, but really what we're saying is 10 to some power gets me back to 645,778, okay? It's not going to be a nice whole number. A lot of times when we deal with logs throughout this chapter, we're going to get an answer that's a decimal. And so we're going to do a lot of rounding to nearest 10th, 100th, 1000th, whatever decimal place we're going to. But that's really what we're asking here. 10 to what power gets me back to 645,778. So if we put the log of 645,778 in our calculator, and you could type it in just like that, what do we get? Let's go to the nearest hundredth. Your log button should be, I think it's on the left-hand side of your calculator for most calculators. .81. Okay, about 5.81. Does everybody know where that log button's at on their calculator? Anybody need help finding it? So that's just a straight plug and chug, right? Plug it into your calculator, get your answer. Your answer is not going to be a nice whole number. What if I said the log of -3? What happens? Error, yeah. And that's because if I said 10 to what power gets me to -3, can't do it, right? There is no exponent that would get me back to a negative number. So what that tells me is I can never ever take the log of a negative number. If I have the log of a negative number, then my answer is no solution. We can't do it, okay? So just something to keep in mind. Doesn't mean your calculator's wrong. Your calculator's telling you, hey, wait a second, you can't do that, okay? What if I have the log of a really small number? What do we get? Okay. And so I show you this one because my answer can be negative, but we can't take the log of negative. Those are two completely different things. So make sure you keep those kind of straight and the difference between those. The negative can't be next to the log, but I could get a negative answer. That means my negative answer is my exponent, right? And if I have a negative exponent, then I take the reciprocal, which gives me a really, really small number in most cases, kind of like we did with 1 over 100 a little bit back. All right, so all of these are what we call common logs. If we use log, then that is what we call the common log. There's two different kinds of logs. The other one that we're going to see is what we call the natural log. And the natural log is going to use ln. And there's a button right next to your log button. That's an ln button, okay? So that's the natural log button. And we'll talk about the difference between these two, but there is some big differences. A lot of the same rules and things apply, but when I have the ln of x, then it's an assumed base of e. We talked about that e number yesterday. My assumed base is e. So what we'll do is anytime we're going to see some problems throughout the chapter that has e in the problem, like especially when we start solving later on, then whenever we have e, we're typically going to use ln. That's going to be the go-to log that we're going to go to. If I have just regular old numbers, common integers, then I'm going to use common logs. But if I have e, then ln is going to be usually my go-to. Now, I could rewrite this using log, but I would have to put a base e in there. Okay, so I could still use our common log as long as I put my base of e down there. Because I can put any base I want to down here. If there's no base down here, it's assumed to be 10. But I could put any number I want down there, and e is a number. So I could put e as a base, and that is, all of those things mean the same thing. Okay, but this is the way we're going to see it a lot of times, because if there is no base, then it's assumed to be e. So those two mean the same thing, but we don't necessarily have to put that e there. But if I were to say, what is the ln, and I'm going to use the same numbers I did over on the right. If I did the ln of 645, 778, just like we did over here, but we did log instead of ln, we can type that one into our calculator. Okay. And that would give us what? 13.38. Okay, 13.38. The reason the answer is different is because my base is different. On log, my base is 10. So we're saying 10 to 5.81 is about 645, 778. Here, we're saying our base is e. Yesterday, we talked about the approximation for e, 2.7 whatever, right? Big, long decimal. So e raised to this power would get me back here. Okay? And you could even try that. You could say, take e and raise it to this power, and it should get you really close to that number. It's probably not going to be exact because this is a round number right here. Okay, but it should get you really, really close. What if I did the ln of -3? Can't do it, right? Still does not exist. Still can't do it. Still a log, just a different kind of log. So no matter what kind of log I have, I can't take the log of any negative number. Okay? So that rule holds true, just like on the last one. If we have the ln of e, my base is assumed to be what? E. Okay? So if my base is e and my log is e, then e to what power gets me back to e? 1. Okay? So this right here is a big one. The ln of e is 1. There's some things in college algebra that whenever I see them from here on out, I'm going to need to know that that is going to hold true all the way through. I squared equals -1 is one that we talked about. Whenever I see I squared from here on out, I know it's really equal to -1. Whenever I see the ln of e from here on out, I need to know the ln of e is really 1. Okay? Much easier to write it as 1 than the ln of e. But that'll be something that we see as we solve log equations. And so that'll be something that comes up a lot. What if I have the ln of 1? My base is still e. What exponent will get me back to 1? 0. Still 0, right? So even though we have a different log, a lot of these rules are still holding true, right? Because my exponent of 0 still gets me 1. E is a number. You got to treat e just like any other number. I know it's not like any other number because it's this big long decimal, right? But it still has a lot of the same rules as well. Okay, we talked about how a log function is an exponential function, or the inverse of an exponential function. And I want to show you how this kind of all plays out. Y equals 5 to the x. We graphed this yesterday, or one very similar to it yesterday, maybe not that exact same function. And I could come up with some real basic equations here, or real basic order pairs, I should say. I could plug in 0. 5 to the 0 is 1. And we said it's always going to cross at 0, 1. I could plug in 1. 5 to the first power is 5. So I could go 1, 5. If I put in -1, we talked about yesterday how it flips it, right? And so that's really 1/5. So -1, 1/5 would be just above the x-axis. So if I graph this, that would be our equation. That is the graph from yesterday. So if we look at a graph of a log, first of all, I could say x equals 5 to the y, because that's the inverse of that original exponential function. But if I were to write this as a log equation, using all the things that we've talked about today, log base 5 raised to the y of x. My circle rule. 5 to the y equals x. 5 to the y equals x. Now, I could put this into my calculator, right? Some of you are able to put this into the calculator just like this. If you don't have the log base button in your calculator, then you won't be able to type this in. So a really quick and easy way that I could graph this function this is the inverse of this. So remember what we talked about on Friday when we did inverses. All I got to do is take those order pairs and flip them around, okay? And so this would now become 1/5, -1, 1, 0, and 5, 1. Same 3 ordered pairs, traded places. So what you're going to find out here is that a log function is just the inverse of what we did. So yesterday, all of our graphs, as long as they were basic functions, crossed at 0, 1. My log functions are always going to cross at 1, 0. 5, 1. 1/5, -1 would be here. Going back to last week when we talked about inverse functions, we said how it flips over that y equals x line, and see how this exponential function has now reflected over that line to be over here. This is your log function. So this is your exponential function. This is your log function. One big difference is yesterday, all of our graphs, we said, are going to have a horizontal asymptote, right? What kind of asymptote does this graph have? What's it approaching?
The Y.
The y-axis. Okay, so it's gonna have a vertical asymptote. So if I have a log equation, it's gonna have a vertical asymptote versus an exponential function that'll have a horizontal asymptote, because we did the inverse of it. Okay. And we won't do a ton of graphs of logs, but that is one thing that we might see. Last, change of base formula. If I have one that's difficult to evaluate, and I ask you to evaluate log 8 base 5, what we're really saying here, using all the things that we've talked about today, is 5 to some power equals 8. Is that a nice, easy integer number? No, right? 5 to the first power is 5. 5 to the second power is 25. So we know our exponent's going to be somewhere between 1 and 2, but we don't really know what it is, okay? So there's a really quick and easy way to evaluate it. And it kind of depends on the type of calculator you have. Once again, I know that some of you have a base button on your calculator, okay? But not everybody does. So if you don't have that base button on your calculator, the really quick and easy way to evaluate this is the log of 8 divided by the log of 5. That's the change of base formula. We're going to take the log of the numerator divided by the log of the denominator, or the base of the log, I should say. What's that give me? If I divide those. Or just put the base in. 1.2. So it's gonna be a decimal. And like I said, we're gonna get a lot of decimal answers for a lot of these problems, because it's not gonna be a nice exact answer. And if I took like 5 to the 1.2 power, depending on how far I rounded it out, then it's going to get me close back to 8. I mean, that's how you could kind of check it. It's not going to give me exactly 8 because we rounded the 1.2 answer, and we wouldn't be able to put that in exactly. If you need help with your calculator, let me know. I'll be glad to help you if you don't know where some of your buttons are at on your calculator. Okay, so the first 15 are just the odds, and then starting at 20, we're going by 5s, and then 75 at the end. Okay. A lot of these are just rewriting it, like we've talked about, not necessarily solving it. Just pay attention to the directions that you've got on there.